probability and probability distribution. Probability theory deals with situations in which there is an element of randomness or chance. The mathematical theory of probability arose in consideration of games of chance but is now widely used in far more practical and applied situations. A random phenomenon is a situation in which we know what outcomes could happen, but we do not know which particular outcome will happen. For any random phenomenon, each attempt or trial generates an outcome. Something happens on each trial and we call whatever happens to the outcome. Experiment is a process of observation that leads to a single outcome that cannot be predicted with certainty.
In this problem, we are trying to determine if we are to spin the spinner 16 times, how many times can we expect the spinner to land on each of the 5 given colors according to theoretical probability? Well, let's examine the green, yellow, and red sections because they are equal in size. We can clearly see that each of these 3 colors occupies 1/4 of the space of the entire spinner. Therefore, the probability of each of these colors being landed on is 1/4, or 1 chance out of every 4 spins. Examining the white and the purple slices, we can see that each one of those occupies 1/8 of the area of the spinner. So we would say the probability of those colors being landed on is 1/8 each, or 1 out of every 8 spins. All of the theoretical probabilities of which we just listed are expressed in lowest terms. We must convert each one of these fractions into 16 because we want to know how many spins out of 16. So all we have to do for green, yellow, and red is to convert the 4 into 16, and for white and purple we also have to convert the 8 into the 16. When doing this, we can see that 1/4 is equivalent to 4/16 and that 1/8 is equivalent to 2/16. The value of the fractions did not change, however we expressed it in terms of 16 spins. So for green, yellow, and red, we could expect to land on each one of those colors 4 times out of 16, and for white and purple, we can expect to land on those colors 2 times out of 16. Now, that's only what we expect. If we actually spin the spinner 16 times, more than likely, we will not land on green, yellow, and red exactly 4 times, and white and purple 2 times. That's why we have something called experimental probability. Experimental probability is determined by actually carrying out the action. So let's spin the spinner 16 times so we can determine what the experimental probability is and then compare it to what we expected. Now let's compare the experimental probability to the theoretical probability. For green, we see that it actually occurred 1 time less than what we expected. For yellow, we actually had it occur 2 more times than what we expected. We expected it 4 and we got it 6. For red, we expected it 4 times, but it only occurred 1 time. For white, we expected it twice, but it happened double that, it happened 4 times. And for purple, we expected it twice according to theoretical probability, and it actually happened twice. So purple is the only color for the experimental that matched the theoretical.
Probability of a single event. If we roll a 6-sided dice, there are 6 possible outcomes, and each of these outcomes is equally likely. A 6 is as likely to come up as a 3, and likewise, for the other 4 sides of the dice, what then is the probability that a 1 will come up? Since there are 6 possible outcomes, the probability is 1/6. What is the probability that either a 1 or a 6 will come up? The two outcomes about which we are concerned are called favorable outcomes. Given that all outcomes are equally likely, we can compute the probability of a 1 or a 6 using the formula probability. Probability is the branch of mathematics that studies the possible outcomes of given events together with the outcomes' relative likelihoods and distributions. In common usage, the word probability is used to mean the chance that a particular event or a set of events will occur expressed on a linear scale from 0, impossibility, to 1, certainty, also expressed as a percentage between 0% and 100%. The analysis of events governed by probability is called statistics. There are several competing interpretations of the actual meaning of probabilities. Frequentists view probability simply as a measure of the frequency of outcomes, while Bayesians treat probability more subjectively as a statistical procedure that endeavors to estimate parameters of an underlying distribution based on the observed distribution.
Alright, let's say we are wanting to know what the weather is going to be like for the upcoming week. At least the work week, that is, or school week. Alright, if we were given the weather report and we saw that Monday is going to be cloudy, Tuesday sunny, Wednesday and Thursday cloudy, and Friday either partly cloudy or partly sunny. So what if I then asked you, what is the probability of it being cloudy this week? Well, what I'm asking you is, what are the chances that it's going to be cloudy? Well, given that we're only looking at the work week, so just 5 days here, we have to first figure out how many days there are in total, which I just mentioned. There are 5 total days. 1, 2, 3, 4, 5. Now, out of those 5 days, how many days are going to be cloudy? Well, 1, 2, 3, and you could argue this one as well because there's a cloud there. So we could say 4 out of the 5 days are going to be cloudy. Now, when we're dealing with probability and we want to figure out what the chance is that it's going to be cloudy, we often deal with percents. So I need to turn this 4 out of 5, or 4/5, into a percent. To do that, I simply divide my 4 by my 5. And when I do that, I get 80%. So at least for this week, the probability that it's going to be cloudy is 80%. Or another way of saying it is, there's an 80% chance that it's going to be cloudy. Now what if I turn things around, and now I'm curious to see what the chances are that it's going to be sunny? Well, once again, I have 1, 2, 3, 4, 5 days total. And out of those 5 days, how many of them are going to be sunny? Well, I have Tuesday, and there is some sun here on Friday, so we can include that one as well. So 2 out of the 5 days are going to be sunny. Now, once again, when we're working with probability, we want to find what the percent is that something's going to happen. So we're going to turn this 2 out of 5, or 2/5, into a percent. So we divide the 2 by the 5. And when we do, we get 40%. So there's a 40% chance this week anyway that there's going to be sunny skies.
A properly normalized function that assigns a probability density to each possible outcome within some interval is called a probability density function or probability distribution function, and its cumulative value is called a distribution function. A variate is defined as the set of all random variables that obey a given probabilistic law. It is common practice to denote a variate with a capital letter. The set of all values that x can take is then called the range, denoted Rx. Specific elements in the range of X are called quantizers and denoted X, and the probability that a variate X assumes the element X is denoted P. X is equal to X. Probabilities are defined to obey certain assumptions called the probability axioms. Let a sample space contain the union U of all possible events EI, so let E and F denote subsets of S. Further, let F is equal to not F be the complement of F, so that F union F is equal to S. Then the set E can be written as probability distribution. Probability distributions are a fundamental concept in statistics. They are used both on a theoretical level and a practical level. Some practical uses of probability distributions are to calculate confidence intervals for parameters and to calculate critical regions for hypothesis tests. For univariate data, it is often useful to determine a reasonable distributional model for the data. Statistical intervals and hypothesis tests are often based on specific distributional assumptions. Before computing an interval or test based on a distributional assumption, we need to verify that the assumption is justified for the given data set. The distribution does not need to be the best fitting distribution for the data, but an adequate enough model so that the statistical technique yields valid conclusions. Simulation studies with random numbers generated from using a specific probability distribution are often needed. A probability distribution is a table or an equation that links each outcome of a statistical experiment with its probability of occurrence.
In a probability distribution, you just make two columns, one for outcome and the other for probability. Okay, let's say you're going to make a probability distribution for the weather this weekend. Let's say that you thought there was an 80% probability that it was going to be sunny, a 10% probability that it was going to rain, a 9.99995% chance that it was going to snow, and a 0.00005% chance that there was going to be volcanic ash. Now, if you add up all the probabilities, they have to equal 100%. Now, instead of the weather, you can make a probability distribution for the economy next year. Let's say that you believe that there's a 20% chance that the economy is going to be great, a 40% chance that it's going to be good, a 30% chance that it's going to be so-so, and a 10% chance that it's going to be really bad. However, saying things like good and great and so-so and really bad isn't really clear. It's better if you can quantify the economic outcome. For example, let's say that if the economy is great, you expect that your business is going to be able to get a 25% return on investment. If the economy is good, you expect that your business is going to get a 15% return on investment. If the economy is just so-so, you figure about a 5% return on investment. And if the economy is really bad, you don't think you're going to make any profit at all, so a 0% return on investment. Okay, the question is, what's the most likely return on your investment? To do this, you just take a weighted average. By taking a weighted average, you can determine the ERR, or expected rate of return. And this is easy. You just multiply the numbers across. You take the probability times the outcome, and then that equals the result. And then you add up the results. For example, 20% times 25% equals 5%. 40% times 15% equals 6%. 30% times 5% equals 1.5%. And 10% times 0, of course, is 0%. Now you add up the numbers in the right-hand column, 5, 6, 1.5, and 0. And you get a total of 12.5%. So after taking a weighted average, the expected rate of return is 12.5%.
Cumulative probability distributions. A cumulative probability refers to the probability that the value of a random variable falls within a specified range. Let us return to the coin flip experiment. If we flip a coin 2 times, we might ask, what is the probability that the coin flips would result in 1 or fewer heads? The answer would be a cumulative probability. It would be the probability that the coin flip experiment results in 0 heads plus the probability that the experiment results in one head. P x is less than 1 is equal to P x is equal to 0 plus P x is equal to 1 is equal to 0.25 plus 0.50 is equal to 0.75. Like a probability distribution, a cumulative probability distribution can be represented by a table or an equation. The cumulative probability refers to the probability that the random variable x is less than or equal to x uniform distribution sample. The simplest probability distribution occurs when all of the values of a random variable occur with equal probability. This probability distribution is called the uniform distribution. Uniform distribution. Suppose the random variable x can assume k different values. Suppose also that the p x is equal to xk is constant. Then p x is equal to xk is equal to 1 by k. Simple and compound events. Suppose we randomly select two people from the members of a club. Look at whether the person selected each time is a man or a woman. Write all the outcomes for this experiment. Probability is the mathematical framework for describing, modeling uncertainty. It is a numerical measure of the likelihood that a specific event will occur. Two or more outcomes or events that have the same probability of occurrence are said to be equally likely outcomes or events. Probability is denoted by P. PE denotes the probability of the event E. What is the probability of getting a spade when a card is drawn from a well-shuffled deck? Let E be the spades. Then we denote the possibility of getting a spade by PE or simply P spade. Calculating probabilities. Classical approach assumes all outcomes of the experiment are equally likely. Let's look into an example of a couple with 3 children and they will at least have 2 boys. Assume that boys and girls are equally likely and that the gender of any child is not influenced by the gender of any other child. The outcomes can be shown in this video.
So this example reads, find the probability that when a couple has 3 children, they will have at least 2 boys. Assume that boys and girls are equally likely. That's an important criteria for the classical method. Boys and girls are equally likely, meaning there's a 50-50 chance of having a boy or a girl. And that the gender of any child is not influenced by the gender of any of the preceding children or subsequent children. So that's a very strong assumption to make, but we need that assumption in order to apply the classical method. And in that case, we would have a sample space that would look something like this. We'd have the first, second, and third child represented. M would represent a male or a boy, and F would represent a female. So this first row is the probability or is the outcome of having a male for the first child, a male for the second child, and a male for the third child. So this would be the probability, or this would be the outcome of having all boys. And as you notice here, there are 8 total outcomes. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 outcomes ranging from all boys to all girls. And since having a boy or girl is equally likely, and also since the probability of having a certain gender of child on one birth is not affected by what happened on a previous birth or a subsequent birth, all of these 8 outcomes are equally likely, meaning each of them has a probability of 1/8. So for instance, the probability of having male, 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 the probability of having all boys is 1 out of 8, because the sample space is size 8, and this is one of those 8 equally likely outcomes. And for instance, the probability of male, male, female is also equal to 1 out of 8. Okay, so let's take a look at the probability when a couple is having 3 children that they will have at least 2 boys. That's the probability that we're looking for. We're looking for the probability of this couple having at least 2 boys. Okay, at least 2 boys. So what we want to do is we want to look at all of the outcomes over here that have at least 2 boys and make the ratio of that number to 8, because there's 8 total outcomes, and of those 8 total outcomes, the number that fit the criteria of having at least 2 boys is what we're going to count. So let's see how many of these outcomes have at least 2 boys. In the first row, I see there are 3 boys. So the first row fits the criteria of having at least 2 boys. The second row has 2 boys also, so that fits the criteria for at least 2 boys. The third row, 2 boys also, so that fits the criteria. Now the fourth row, there's only 1 boy. The oldest is a boy, but the middle and the youngest child are 2 girls, so that one does not fit the criteria for at least 2 boys. Let's see here. The fifth row, that one has at least 2 male children, 2 boys. The sixth row, only 1 boy, the middle child. The seventh row, only 1 boy, the last child. And the third row, there is no boys at all. There are no boys at all. So therefore, the probability of having at least 2 boys, if you look over here, there are a total of 8 possibilities for having 3 children, 8 possibilities for the outcomes. And of those 8 possibilities, which would be the denominator of the fraction, 3 out of those 8 would be outcomes that are favorable to having at least 2 boys.
Relative frequency approach. Probability of E may be interpreted as the relative frequency of the E over a long series of experiments. Law of large numbers. If an experiment is repeated again and again, the probability of an event obtained from the relative frequency approaches the actual or theoretical probability. Probabilities must be between 0 and 1 inclusive. A probability of 0 indicates impossibility. A probability of 1 indicates certainty.
X is equal to the number of heads after 100 tosses of a fair coin. Tosses or flips of a fair coin. The law of large numbers just tells us, well, first of all, we know what the expected value of this random variable is. It's the number of tosses, the number of trials, times the probability of success of any trial. So that's equal to 50. So the law of large numbers just says if I were to take a sample, or if I were to average the sample of a bunch of these trials, so I get, I don't know, my first time I run this trial, I flip 100 coins, or I have 100 coins in a shoebox, and I shake the shoebox, and I count the number of heads, and I get 55. So that would be x1. Then I shake the box again, and I get 65. Then I shake the box again, and I get 45. And I do this n times, and then I divide it by the number of times I did it. The law of large numbers just tells us that this average, the average of all of my observations, is going to converge to 50 as n approaches infinity, or for n approaching 50.
Conditional probability. The conditional probability of an event B is the probability that the event will occur given the knowledge that an event A has already occurred. This probability is written P B by A, notation for the probability of B given A. In the case where events A and B are independent, where event A has no effect on the probability of event B, The conditional probability of event B given event A is simply the probability of event B, that is PB. Bayes' theorem. Bayes' theorem describes the relationship that exists within an array of simple and conditional probabilities. In order to explain the Bayes formula, let's see another video. Summary. Probability is the branch of mathematics that studies the possible outcomes of given events together with the outcomes' relative likelihoods and distributions. Statistical intervals and hypothesis tests are often based on specific distributional assumptions. Before computing an interval or test based on a distributional assumption, we need to verify that the assumption is justified for the given data set. A cumulative probability refers to the probability that the value of a random variable falls within a specified range. The conditional probability of an event B is the probability that the event will occur given the knowledge that an event A has already occurred. Bayes' theorem describes the relationships that exist within an array of simple and conditional probabilities.